Testing. Testing. Oh, there it goes. Hello. There's that. Alrighty. So I guess we're going to start a little bit closer to 5:30 because we're being televised to the Okeechobee campus too. But in case you guys haven't done so already, go ahead and pick up some papers. There's a questionnaire, like a regular basic worksheet, and a, what's that called, like an evaluation, along with a sign-in sheet up there. So if you guys haven't grabbed all three of those papers, go ahead and do so now and sign in, please. Okay. What do I do? Blank paper. There's that. No, you're too. Alrighty. Let's go ahead and begin. Hello, hello. Welcome, everybody. Thank you guys for coming. My name is Mary Higgs. I am an instructor with the ASC Center. I have my bachelor's in chemistry from UCF with a minor in physics. I've been teaching here for IRSC for the past 2 years. I do the chemistry and physics departments for the ASC tutoring, and I've been teaching physics labs for the past year. My job here is to make sure everybody understands the basics of general chemistry. A lot of this should be review from either high school or college classes, stuff you've seen before, so there shouldn't be a whole lot of new information. If you're coming to the physics one, which is in 2 weeks after spring break, it's probably a lot of new information. I don't feel a lot of people have had physics before. But this one should be nice, fun, easy. Try to break up with a lot of like pictures and videos to adapt to everyone's learning styles. There's also an evaluation that's with your handouts. I love hearing feedback. This is my second time only doing the presentation for chemistry, and if I can help you guys learn it all, please let me know. Okay? So today we're going to be discussing just general topics from chemistry, whether it's balancing equations, turning a periodic table, how to use the periodic table, because the periodic table was not created on accident. They didn't just throw a bunch of elements out there and decide they're going to go there. They are on an arrangement because of their bonding capabilities. So reading your periodic table and knowing how to use it is essential for chemistry. All right, so let's go ahead and begin. Okay. So let's see, let me put this over here. Beautiful. Okay, so what is chemistry? Chemistry is a branch of science that deals with identification of substances of which matter is composed. And atoms are what all matter is made up of. They're the smallest units of an element that will retain its properties. So the study of chemistry is you want to determine how all of these atoms are going to interact, combine, and change. Molecules are 2 or more atoms, and then matter is a substance that has a mass which occupies space. Atoms are going to make up the smallest unit of the element. So the atomic structure, what is an atom? An atom is made up of a nucleus and surrounding electrons. So your nucleus is going to have protons and neutrons in it, which are going to be the weight of that element. You're going to have electrons floating around the outside of it. Those electrons are what's responsible for the bonding properties of that element. There's a chart up there which you can see. So you have a proton, which has a positive charge, and it weighs 1 atomic mass unit. Neutrons are neutral, so they have no charge, but they still have a weight of 1 atomic mass unit. An electron is negative, but also is massless. Its mass is very negligible. It's something like ridiculously small. That doesn't really matter when it comes to weighing. Plus, they kind of transfer and go all kinds of different places, so we don't really worry about those too much. When it comes to weight of your atom, you're going to worry about just the masses of the proton and neutron, and then the electron would be its charge. So the periodic table. The periodic table was first created by Dmitry Mendeleev, a Russian chemist, back in 1869. Today, there are 118 atoms that are known. The way he arranged these were, he noticed that there were all these elements that reacted the same and did all the same stuff. So he decided to go ahead and arrange these in different groups and rows. Now, notice here that they do kind of skip a little bit. They're all going to go reading from left to right with increasing atomic number. The atomic number is going to be the number of protons in that atom. It is essentially the atom's identity. The reason why I skipped different parts is because of their bonding properties. So different groups are all going to have the same identity. So when you read a periodic table, you have, of course, your elemental symbol. Chemists are lazy, and what we want to do is we want to shorten everything down. So instead of writing out helium, for example, we'd be writing out the chemical symbol for helium. The chemical symbol is always started off by a capital letter, and then it's followed up by a lowercase if that is the case. So if there's 2 or 3 word or letters in the symbol, the last 2 are going to be lowercase. So the first one is always uppercase. So you have a couple things over here that are good for figuring out what's going on. You have the atomic number, which is the number of protons. Once again, this is the atom's identity. If you change the atomic number, you change the element. So going back to the periodic table, we had up here helium with a number 2. So if I were to add 1 extra proton on, I would be back over here at lithium, number 3. Adding another proton brings me over here to beryllium, number 4. So that's why atomic number is very important, its identity. The mass number is going to be basically the mass of the element or what's in the nucleus. That's the only thing that has the mass out of the atom. So it's going to be the number of protons and neutrons in your element. Isotopes. Isotopes, you can think of synonymous as heavy. Once again, so since they're heavy, the only thing that holds mass is a proton and a neutron. If you change the protons, you change the entire element. But we have carbon here, and it has 3 different weights. That's because you're just adding on neutrons onto your nucleus. So for example, carbon-12. Carbon-12 would have 6 protons because that's carbon's identity. So 6 minus your 12, which is the weight of this isotope, then makes it 6 neutrons. Going on to carbon-13. Carbon-13 is going to have, of course, the 6 protons because that's the chemical's identity. And then minus the 13 is going to be 7 left over. That means we're adding on 1 extra neutron, making it a little heavier. Carbon-14, same thing. We're going to take their 6 protons, which is carbon's identity. We're going to subtract them from the whole mass of 14, leaving it with 8 neutrons. Ions. Ions are synonymous with a charged particle. So there's 2 different types. There's anions and cations. Anions are negative. They gain an electron, and cations are positive, which means they lose an electron. So think about that. This is why electrons, I know personally for me, they were kind of confusing when I first started learning. If it's gaining a negative charge, it's making that element more negative. All right? And if you're taking away something that's negative, you're getting more positive. And that's where the kind of opposites come into play over here. Like I said, a little bit confusing, and when we get into oxidation and reduction, hopefully there's a video that'll clear all that stuff up for you guys a little more. Okay, so the periodic table. The periodic table is arranged in groups. Groups are your columns. And all these columns, all the elements in each column are going to have the same reactive properties. Periods are going to be the rows. Electronegativity is a special quality of elements. Electronegativity is the wanting of electrons. So fluorine is the most electronegative element, which means that fluorine is going to hog the most electrons. It wants them so, so bad. And it sprawls out almost like an ombre effect throughout the periodic table. So fluorine up here would be the most electronegative, along with all these. And down here would be the least electronegative, which means that anything down over here, they're wanting to give away their electrons. Like they don't want them. Up here, they want to hog them all. And this is going to be very important when it comes to bonding later on. So the groups of the periodic table are kind of special. The first one is called the alkali metals, and it's going to be in group 1A. Group 1A means it has one extra proton to give away. We'll read about this in a little bit. The alkali earth metals are going to be in group 2A, which means they have 2 electrons to give away. Traditional metals are down here in the pink. They're just kind of weird, and they do their own things, so we don't really group them into anything as far as their own bonding capabilities. They all have different charges and stuff, and they get kind of crazy. So here's the metalloids. This is going to be your metal line. Metalloids are going to have properties of both metals and nonmetals. This is going to be important for bonding later on to determine whether a bond is ionic or covalent. You have your basic nonmetals, which is groups 4, 5, and 6. So with the charges, we have charge of 1+, which wants to give away 1. Group 2A wants to give away 2 to make itself more positive. Skipping all these guys, jumping over here to boron. So boron's going to be in 3A, and that's going to have 3 electrons to give away. Carbon is going to be in group 4, and that's going to either take in 4 or give away 4. So nitrogen is going to have 3 to give away, so it's going to be -3 charge. Oxygen is going to have 2 to give away, so it's going to be -2 charge. Fluorine is going to have 1 to give away, so it's a -1 charge. And the noble gases don't react. We're going to get into all this here in just a second. The noble gases don't react. This comes from the octet rule and Lewis dot structure. So I want you guys to all notice, back over here, we have the entire first row right here from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon all the way through. Going on to their Lewis dot structures. We said that lithium was in group 1A. It has 1 electron to give away. All elements always want to have 8 electrons in their valence shell. So is it easier to take in 7 electrons or to give away 1? Give away 1, right? So if it gives 1 electron away, that would give it a +1 charge, because it's giving away something that's negative. So going up here to beryllium, which is the next one over in group 2A, is it easier to take in 6 to meet your 8, or is it easier to give away 2? Give away 2, right? So if you give away 2 electrons, give away 2 negative things, you're going to have a +2 charge. So that's why electrons are a little bit backwards in the way they work. And this is what's going to go on through this entire little system. So when you go here to carbon, carbon can either give away its 4 or take in 4. It's the same thing. Nitrogen, it's going to have 5 valence electrons because it's in group 5A. So nitrogen wants to take in 3 electrons. It's easier for it to take in 3 electrons than to give away 5. So if it takes in 3 electrons and meets its whole 8, it's going to have 3 extra negative charge, give it 3 negative. Same with the oxygen. It's going to take in 2 electrons to give it a -2 charge. And then fluorine is going to take in 1 electron to give it a -2 charge. From the periodic table, whenever it was in groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, and the noble gases, that just means that's the number of electrons in its valence, which goes with the reactive properties that Mendeleev decided. Okay, there's some special formulas I want you guys to kind of look at. Most chemistry classes should have you memorize these. I'm not sure if the NLN is going to have you memorize them or just kind of recognize that they are polyatomics. So poly means many and ionic means charged. So this means that this is a many atomic compounds with a charge. And there's several over here. It's a nice little pretty chart. Like I said, I'm not really too sure if they're going to make you memorize this or not for the NLN, or just recognize that these are little compounds. So basically, whenever you see these in a formula or in a compound, understand it takes a lot to break these guys apart. So these are always going to remain a compound. So if you're balancing anything, or if you're kind of looking at a whole molecule and the way it's going to react, whether it's displacement reaction or decomposition reaction, whatever the case is, treat these as their own molecule. So if you had carbonate, for example, if you're going to be counting them, you have 1 carbon and 3 oxygens, of course. But if you have carbonate whenever you're doing a reaction, treat the carbonate as its own like little product. And we're going to get to some examples of those later on when we go into reactions. So an element versus a compound. The difference between the two is that compounds can be simplified. Now, trick question. If I give you guys a diatomic molecule, like we'll say O2, for example, is that a compound or an element? It's a compound, right? Because you can take that O2 and split them up into different oxygen atoms. So oxygen just by itself would be an element. So to calculate the mass of a molecule, it's not too difficult. I always like doing it with this little chart over here, so people have different ways to do it, whichever gets the job done. I have the example over here of CaCl2. So you list your elements. I have a Ca and I have a Cl. The atomic mass is what you find in the periodic table, what they weigh. So from the periodic table, I know that calcium weighs 40 grams, and I know that chlorine weighs 35.5 grams. You're going to multiply it by the number of atoms that are in this molecule. So if I have 1 calcium, and I'd have 2 chlorines, that would give me 71. Add these totals in together, and that would give you 111 grams. So the best way to do this is with practice. You guys want to go ahead and practice doing this one real quick? The answer is on the screen. This is a glucose molecule. It's C6H12O6. Any sugars, you're always going to see, is good for nursing too. You recognize the sugar. They come in C's, H's, and O's with the basic structural formula of C1H2O1. So if you multiply a 2 through there, it'd be, C2H4O2. Multiply a 3 through there, it'd be C3H6O3, etc. And those are all sugars. So when you guys are doing this, you see that carbon is going to be 12 grams, hydrogen is going to be 1 gram, oxygen, you can round it to 16 for purposes, but technically it weighs 15.99 grams. Now teachers are talking about that kind of stuff. When you get your answer, you should be at 180 grams. If you have any questions about that, you can go ahead and see me afterward, or come to the ASC Center for extra practice. Okay, so a chemical reaction. A chemical reaction involves reactants and products, which means that 2 things are going to react and they're going to produce something. Okay? They're usually depicted in these little equations, these chemical equations, which once again we use the element symbol along with a bunch of numbers to determine what's going on. So any of these bottom numbers down here, these lower numbers, affect just that element in question. Any of the coefficients or the big numbers in front of the molecule multiply through the entire molecule. So for example, if you have just 1 down here, there's no number, it means it's a 1. You need to have 4 aluminums. 3 times 2 would be 6 oxygens. 2 times 2 would be 4 aluminums. And then 2 times 3 would be 6 oxygens. And that's how you would see that. This is a balanced chemical equation. All right, we're going to watch a video real quick on how to balance equations.
How to balance chemical equations in 5 easy steps. Step 1, count the atoms on each side of the equation. Let's count each type of atom. Sulfur, I have 8. Oxygen, I have 2. On the product side, sulfur, I have 1, and oxygen, I have 2. Note that if there's nothing after an element, we assume that to be 1. And that's it. We're done with the first step. Smooth. The big rule for balancing equations is that we can only change the coefficients. Those are the numbers in front of the atoms. The numbers after the atoms, the subscripts, cannot be changed. So let's balance this equation by changing the coefficients. If there's no coefficient written, we assume that it's 1. So right now there's a 1 in front of each of these terms. We can see that we have 2 oxygens on each side of the equation. So the oxygens are fine. But the sulfur atoms, we have 8 on the left side, the reactants, and only 1 on the right. Well, to fix that, I can change the coefficient in front of the sulfur on the right and make that an 8. So if I put an 8 here, that means 8 times the 1 sulfur. That'll give me 8 sulfurs. And now my sulfurs on both sides are 8. But this 8 here is also times the 2 oxygens. And that gives me 16 oxygens. So I've fixed the sulfurs, but the oxygens aren't balanced. I can change the coefficient here, though, to 8, because 8 times 2 equals 16. So now I have 8 sulfurs on each side, and I have 16 oxygens on each side of the equation. This equation is balanced. Step 3, so you don't forget, only change the coefficients. Let's try another problem. So in this equation we have 2 hydrogens, 2 oxygens, over here 2 hydrogens, and 1 oxygen. How about, let's see, I'll put a 2 right here. So 2 times 2, that gives me 4 hydrogens, but 2 times the 1, that'll give me 2 oxygens. So my oxygens are balanced now, but my hydrogens are messed up. What I can do over here is put a 2 in front of hydrogen, and now 2 times 2, that'll give me 4. And now the atoms on each side of the equation are the same. This equation's balanced. Sometimes we'll have equations that look downright scary. Yikes. But if we have a polyatomic ion on both sides, like the SO4 or the NO3, then we can consider that ion to be just one thing. Let's see how that works. So here's the equation, and I've done my accounting below. You can see I have 1 calcium here, 1 calcium over here, and then I wrote the entire SO4 as one thing. And I have 1 of those here, and over here I have 1 SO4, NAs, 1, 2 NAs on this side, and over here 1 NO3, and I have 1 NO3, but that 2 on the outside means I have 2 of them. So I have 2 NO3s. So if I put the coefficient of 2 right here, that means I'll have 1 times 2, 2 NAs, but this 2 also multiplies across, so 1 times 2 for the NO3s, that gives me 2. And now everything is balanced. So by treating those polyatomic ions as just one thing, it makes it a pretty simple equation to balance. Let's wrap up with one that sometimes gives people problems. So we can see we have 1 carbon, 4 hydrogens, and 2 oxygens. Easy. Over here we have 1 carbon, and then we have 2 oxygens, and then we have 2 hydrogens. But be careful. We have to count this oxygen over here as well. So we have 2 plus 1. That'll give us 3 total oxygens. I'll start by balancing the hydrogens. If I put a 2 in front of this hydrogen, 2 times 2, that'll give me 4. And that'll fix the hydrogens. But now I have 2 oxygens plus 2 times 1, 2 oxygens. That gives me a total of 4 oxygens. But that's good, because now if I put a 2 right here and change this coefficient, 2 times 2 equals 4, and now everything is balanced. This video has given you the basics for balancing equations, but you've got to practice to gain speed and expertise. The more you practice, the easier it becomes. This is Dr. B, and thanks for watching.
Okay, cool. So you guys saw how there was polyatomics and stuff in there, and how they count the polyatomics just as one giant element to make matters easier. There's a little sheet in your in one of the packets you guys picked up that'll give you a practice for balancing equations too. So that way you can practice at home. If you have extra problems, you can always come to the ASC Center. We have extra problems for you over there too. Okay? So the rate of a reaction. The rate of a reaction are going to depend on two things. They're going to depend on two substances. They must come in contact. And you have to have enough energy in order to have the reaction happen. So factors that affect this, there's six different factors. There's the concentration of the reactants, there's catalysts, temperature, light, particle size, and pressure for gases. So a catalyst is something that's going to decrease the amount of energy needed to make a reaction happen. What it basically does, and it doesn't get used up either, so it goes in, reduces the rate of the reduces the activation energy required for the reaction to happen, and then it comes right back out as itself. It never actually reacts. It just lowers the activation energy. Equilibrium. Most reactions don't go to completion. They rather reach an equilibrium, which is the rate of the forward reaction is equal to the rate of the reverse reaction. So your products and your reactants are going to kind of even out, and they're going to kind of evenly distribute in there. Out of these pictures, A, B, or C, which one would depict an equilibrium? B is correct, where it has an equal number of blue fish and black fish that would be in that little tank. There's four main types of reactions that you're going to be asked about. There's synthesis or combination, decomposition, single replacement, and double replacement. So synthesis or combination is just what it says right there. It just says you're going to take two products, A and B, and you're going to combine them together to form giant product AB. So we know from colors, we know that red and yellow equals orange. That's the way to think about it. Decomposition reactions is just the opposite of that. So you would have your product BC, and you can decompose it into products B and C. So like a purple over here separates into blue and red. Single replacement reactions is whenever you're going to have a swap of partners, way to call it. So from the equation down over here, we have A and B plus C is going to yield A and C plus B. So C and B are going to swap places, like you see right here in the picture. Double displacement is where you're going to have the swapping of two partners. So A and B and C and D, you're going to switch those out, and you're going to form new products of A and D and C and B. As you can see over here with the pictures, they're just using the swap partners. And if you guys do a couple of problems of these, you'll be able to actually determine like what's going on like really easily. It just takes a lot of practice. Special type of double displacement reaction occurs with neutralization. When you have an acid and a base and you put them together, they're going to neutralize out. They neutralize out to a salt and a water. A salt is a combination of anything from group 1 and group 7. So NaCl is an example of a salt. Potassium bromide over here is an example of a salt. Group 1 and group 7. So your acid is anything with the H plus ion. A base is anything with the OH ion. What's going to happen like in this top reaction? You're going to have your H and your Cl, Na, and then this polyatomic OH. So it says A and B, C and D. And you're going to get the opposite reaction of C and B, and then this H2O is kind of this OH right over here, and this H to give you the H2O. Just kind of written a little bit differently. So there's special kinds of reactions. Sometimes when you react things, they get hot. Sometimes you react things, they get cold. What does that mean? So an exothermic reaction is whenever you mix two things together and it's going to get super hot in your hand. If you're holding like a glass in your hand, it's going to get really hot. So it's going to release energy into the surroundings. So if you're releasing energy into your surroundings, that means when you react these two things, it has an excess of energy and it's going to expel it. Therefore, your reactants are going to have more energy than your products to give you that heat expulsion. If you have an endothermic reaction, on the other hand, it's going to get cold in your hand. There's certain reactions where you'll see them and they'll literally just turn almost to ice. So what happens there is you get your two products in together. In order to get that product's going to require a lot more heat than what the reactants are able to give it. So in order for it to form the product, it takes in heat from the surroundings, therefore making it cold to the touch because it's absorbing all the heat in. Right? So ionic bond is basically a metal and a nonmetal. Remember from the periodic table where we had that nice little metal line that went through? That's where you can determine where your metal and your nonmetal are going to be placed in the periodic table. Once again, always really important to use your table and use everything you know about it. Sodium chloride is the famous ionic compound. Sodium has 1 to give away because it's in group 1A. Chlorine has 7 valence electrons, therefore it just needs 1 more to get its 8. So if sodium gives away its 1, so taking in 7, chlorine takes that 1 to form its 8, and then both are happy. Covalent bonds, however, are between two nonmetals, and they share electrons. Here's an example right here of fluorine. Fluorine is going to be in group 7. Therefore, they both only need 1 in order to make their 8. So they're just going to pass this 1 back and forth super, super, super fast to where it's almost like it's within its same orbital. So it's sharing the electrons. Here's a picture of H2, which is another one where it just kind of binds and it just passes that along really, really fast right there, to form a covalent bond. So covalent bonds can either be nonpolar or polar. So the technical way to look at this with the old math and everything is look at electronegativity. Remember how electronegativity was the really wanting of an electron, and it's like who wants it more is basically what it is. So each element, if you're going to have this problem on a test with the math part, they should give you each element's individual electronegativity. And all you do is you subtract them. It's that easy to form these numbers down here. So the way I always saw it, though, whenever I was going to school, is whether they're symmetrical or not. So you have two CLs over here. They're basically a giant mirror image, and they're going to be sharing things evenly. So it should be okay. If you have this oxygen, these like super positive hydrogens over here, then you're going to see that the oxygen is going to want to hog those more because these are kind of positive, that kind of stuff. But if you ever get confused, you can do the math down here, which is a 3.44 minus a 2.12 to show you that it's to get this number down here. Now, what do these numbers mean? All right, skipping a slide. So what this means is you're going to have your 3 different bonds, the covalent bonds, the covalent, polar covalent, or ionic. The electronegativity difference for each of these would be that number that you get whenever you subtract the 2 from that one bond. And if it falls in this range, then that's the bond type it is. And so the covalent nonpolar is basically almost a small difference. The polar covalent is going to be a small difference, and the ionic is going to be a very large difference. Like we said here earlier with the NaCl, chlorine was over there next to fluorine, and it's super, super electronegative. And then sodium is over there on the group 1 side, and it's in that like metals where it's not really wanting the electrons, wants to give them away more. And that's where you get into that. Okay, so back to that previous slide with the bonds. So whenever you have a bond, they're usually depicted with these lines in between each molecule or each element. If you have a single bond, that means that they are sharing, they have 2 electrons that are being shared. Double bond means they have 2 pairs or 4 electrons that are being shared. Triple bond means they have 3 pairs or 6 electrons that are then being shared. A dipole, by definition, is an unequal distribution of charge. One end is positive and the other end is negative. Dipoles are going to attract each other, like a magnet does. If you have a magnet that has a positive and negative end, they're going to attract each other. Same thing with molecules. They have higher melting points and boiling points than other nonpolar molecules. And a very special type of this is called the hydrogen bond. Water is a famous example of this, and this is why water is pretty cool. So water is actually a bent molecule. Whenever you see that, so going from the Lewis dot structure of oxygen, we know that it has 6 because it's in group 6, right? 1, 2, 3, 4, 5, 6 valence electrons, right? And so it just needs 2 to make up the 8. Where are these 2? Right here. And it's going to form with hydrogen to make that water molecule, making it a bent molecule. These electrons essentially push your hydrogens into each other to give it that like weird L-ish kind of shape. So if these are electrons over here, this is pretty negative, right? And these are your hydrogens over here are pretty positive. That's the polarity of a molecule. So what's going to happen, we have a bunch of these things in together. You're going to have your negative end sticking to your positive end, and that's going to be a nice little chain reaction of all that stuff. And that's the hydrogen bonds when it comes together. All right, so fission and fusion. This kind of strikes close to home because we do have the nuclear power plant over here. Nuclear power plant is run by nuclear fission. Fission is a separation of a molecule to release energy. So like the example that they give you is that they bombard uranium ions with neutrons and it spreads it apart. Fusion, however, is the opposite of that, and it's fusing 2 atoms together. The famous example of that is any of our stars. They use deuterium and tritium, which are 2 isotopes of hydrogen, I believe, or helium. No, 2, yeah, that's right. They're 2 isotopes of hydrogen, and then they come together to form helium, because that's where you see the positives over here. Yeah, the H2 and the H3. So that's what happens with our stars. If you guys see stars glowing, that's the light being produced, and all light is energy, so therefore the fusing of the 2 atoms is energy. Also, fission produces energy because we have light in our homes. So a half-life, a radioactive half-life. So whenever you have your starting 100%, each radioactive element is going to be completely different. And sometimes it'll take them 20 years to decompose into a half-life, or sometimes it'll be 20 seconds. Everyone's different. Whatever your half-life is, though, understand that that half-life means it's going to take, we'll say half of it is 1 year. It's going to take 1 year for half of whatever your isotope is to decompose into half of it. Another year, and half of that's going to be gone. Another year, and then half of that amount's going to be gone. So it's whatever it takes for it to take your amount and cut it into half. And that can go on and on and on forever. Like I said, sometimes they're 20 seconds, sometimes they're 20 years. It literally depends on everything. So oxidation reduction reactions, we like to abbreviate these as redox reactions. These are going to be electron reactions. So we like to use a couple of acronyms. Oxidation is loss of electrons. Reduction is the gain of electrons. Or you can say the Leo says GER, which is loss of electrons, oxidation, and gain of electrons is reduction. There's a short video, because this stuff does get kind of complicated. It always confused me. I was going through school too, because I'm like, it's gaining, but then it's getting like more negative, and it gets kind of confusing. There's a really great video here I want to show you guys. This guy's really cool face about the oxidation reduction reactions.
The electron is to chemistry what money is to capitalism. It's all about who has it, who wants it, and what they're willing to do to get it. Electrons are what make it possible for an atom to bond with other atoms to form molecules, and when that happens, a tremendous amount of energy can be exchanged in the process. But not all chemical reactions involve electrons changing hands. Acid-base reactions, you'll recall, are more about swapping protons. But because electrons are the real coin of the realm in chemistry, the most important reactions that take place on Earth involve the transfer of one or more electrons from one atom to another. These are redox reactions. Redox, which is a portmanteau of reduction oxidation. But what's up with those words? You know what reduction is, making less of something, and then oxidation maybe has something to do with oxygen. Well, sometimes, but not always. These are actually super terrible choices for what is actually happening in redox reactions, but we are stuck with them. Reduction is when a substance gains electrons. Yes, it gains, which is the opposite of what the word reduce means. Fantastic. And yes, sometimes I want to punish the people who named these things so inaccurately, but they didn't know any better and they're all dead, so we can't do anything about it. Proto-chemists would make pure metals by heating or smelting their ores. And they noticed, during the smelting, that these substances would become lighter. So I guess it's not crazy that they decided to say that these substances were being reduced. Our old French friend Antoine Lavoisier figured out that this was because oxygen gas was actually leaving the compound, making it lighter. What he didn't know was the actual chemistry involved. Oxygen is, unsurprisingly, the quintessential oxidizer. It pulls electrons off of one molecule to make itself more stable. But if you heat it up enough, it gets all energetic. Today, we understand that oxidation and reduction are all about electron transfer. So you might think that we'd rename them, and some chemists have tried producing terms like electronation and de-electronation. But once a set of terms is decided upon and used for a while, it's pretty difficult to uncreate it. So we're stuck. To keep these seemingly nonsensical names straight, I rely on the phrase oil rig. Oxidation is loss of electrons, reduction is gain of electrons. We just gotta know this stuff, because it's everywhere. When your cells convert sugar into energy so you can move and breathe and think, that's redox. When plants photosynthesize sunlight into food, that's redox. The battery powering your laptop? Redox. Fire? Also redox. Since electron swapping is the name of the game here, when you study redox reactions, it's important, critical, absolutely essential to keep track of the electrons. Think of them as dollars or pesos or pounds or euros. In any transaction, one person is going to gain them and the other is going to lose them. And to stay on top of things, you have to keep tabs on who's ahead and who's behind. Atoms are fond of sharing electrons, though, forming covalent bonds, so sometimes keeping track of where they are and where they're going to end up isn't quite so simple. Let's think of every covalent compound like a marriage, though it's going to be a weird marriage, because there might be 6 people in it, sometimes the same person several times, without commitment, no commitment, and also no emotions. Don't think too much about it. Like in a marriage where money gets shared, covalent compounds share electrons. The trick is figuring out who gets the cash when the vows break. So we've created a useful little system assigning electrons 100% to atoms that are actually at the moment sharing them. The number that we assign is the atom's oxidation state, or oxidation number. Even though we are of course aware of covalent bonds and the sharing of electrons, the processes are easier to follow if we imagine that the atoms are already splitting up the bank account, as if they were in an ionic or non-sharing bond. So an atom's oxidation number is basically what its charge would be if it actually owned all of its electrons exclusively, like the newly minted bachelors that they may become. So to figure out those oxidation states, or oxidation numbers, we have some simple rules for some atoms. First, the oxidation number for any element by itself, whether it's monatomic or diatomic or polyatomic, like an atom of calcium, or a molecule of H2, or an even bigger molecule of sulfur S8, the oxidation number is 0. Atoms, by definition, do not have a charge. If they had a charge, they would be ions, and if they're sharing with themselves, they share equally. Second, for a monatomic ion, basically a charged atom, it's simply the size or number of its charge. So the iron 2 in Fe2+ has an oxidation state of +2, while a chloride ion is -1. Third, oxygen, which is unsurprisingly all over redox chemistry, almost always has an oxidation of -2, unless it happens to be in a peroxide molecule like hydrogen peroxide. hydroxide. Fourth, hydrogen is +1. And fifth, fluorine is -1, as are all the other halogens most of the time. Pretty much unless they're bonded to fluorine or oxygen, because fluorine and oxygen are so bad that they can make anybody's oxidation number positive, if you know what I mean. And those are the rules. That's all you need to know. Now, the total of all the oxidation numbers of all the atoms in a neutral compound will add up to 0. Like water with 1 oxygen with a -2 oxidation state and 2 hydrogens at +1, and voila. The neutral compound has an oxidation number of 0. A polyatomic ion, on the other hand, has to work out to have an oxidation state that matches its charge. So SO42-, the sulfate ion, has 4 oxygens for a total of -8, but we don't have a rule for sulfur, so I guess we just give up and walk away. Who cares anymore? No! We use like 3rd grade algebra because we have to end up with an oxidation number of -2 for the whole compound. We know that sulfur, in this particular compound, has an oxidation state of +6. But sulfur's oxidation state isn't always +6, and that's why we don't have a rule for sulfur, or a lot of other elements for that matter, because oxidation states of most elements change depending on what they're bonded with. Now we can use this same logic to figure out what happens when these compounds interact in redox reactions. Molecular divorce courts of electrons changing hands, being haggled over and traded, with some players taking big profits while others lose nearly everything. Them's the breaks. Let's start out with a simple example. A chemical reaction that I believe has saved more lives than any other in the history of chemistry. Created by a war criminal to blow people up during World War I, the Haber process. The Haber process removes the ultra-stable elemental nitrogen from the air and combines it with hydrogen to form NH3, ammonia, for use in bombs and also in fertilizer, increasing the carrying capacity of the Earth by billions. Nitrogen in the air exists as elemental diatomic nitrogen, and hydrogen likewise is also diatomic H2. So we know that starting out, all of the atoms have an oxidation state of 0. The product of the reaction, ammonia, is a neutral compound with 1 nitrogen and 3 hydrogens. The hydrogens each have an oxidation state of +1, remember the rules, so nitrogen must have an oxidation state of -3. Nitrogen thus gained electrons, its oxidation state went down, and so it was reduced. So at least when talking about what oxidation states are doing, the word reduced makes sense. Hydrogen lost electrons, the oxidation state went up, and it was oxidized. Now this is a pretty simple equation to balance, but redox equations can be a huge headache sometimes because of the number of individual atoms involved. So we often have to balance them in half reactions. So even though we don't really need to do the half reactions because this is a pretty simple equation, we're going to do them anyway, just because it's an example that's simple to start with. So start out with the nitrogen getting reduced. We have N2 with an oxidation state of 0 becoming NH3 with an oxidation state of -3. First, we balance the number of nitrogens, then add the number of electrons that we need to have there be the same number of electrons on each side. Do the same with the oxidation half of the reaction, and then combine them to get your whole reaction with the electrons canceling out. Now yes, maybe that seemed like an unnecessary step, but allow me to show you a more complicated example that will prove how necessary it may be. In this flask is silver diamine. We're going to use some redox chemistry to get the elemental silver out of it nice and clean and shiny, and it's not gonna be no simple Haber process. The silver diamine is going to react with an organic aldehyde, any aldehyde actually. The business end of the aldehyde is the CHO end. The R in organic chemistry is a symbol for some organic group of atoms, and in this reaction, those atoms don't matter. The silver diamine reacts with the aldehyde and hydroxide, creating carboxylic acid, ammonia, and water. First, let's assign ourselves some oxidation states. The silver is in a complex with 2 neutral ammonias that are going to remain unreacted throughout the equation, so we can treat them like a single species with an oxidation state of 0. Since the silver diamine has a charge of +1 and the ammonias don't affect that, silver's oxidation state must also be +1. The aldehyde has 1 hydrogen at +1 and 1 oxygen at -2, but is neutral overall, so the carbon must be +1 as well. The hydroxide ion is simple, -2 for the oxygen, +1 for the hydrogen, and an overall charge and thus oxidation state of -1. On the reactant side, the silver is now atomic, so its oxidation state is 0. The carboxylic acid has 2 oxygens and 1 hydrogen, so the carbon now has an oxidation state of +3. NH3 remains at 0, and the hydrogen and oxygen of water also haven't changed oxidation states. So silver's oxidation state decreased or was reduced from +1 to 0, while carbon was oxidized from +1 plus 1, 2 plus 3. Half reaction time. Silver was reduced, gaining 1 electron, forming elemental silver and ammonia from silver diamine. The aldehyde was oxidized, forming carboxylic acid and requiring 2 electrons. With the help of those electrons, we know that at the very least we have to double the reduction half of the equation entirely in order to get the right number of electrons on both sides. We do that, and oh god, that's good stuff. And we combine them together for a perfectly balanced redox equation. And now, watch me take those electrons and turn them into money. And there you have it, folks. That is pure silver coating the inside of the flask. Thank you for watching this episode of Crash Course Chemistry. If you were paying attention, you learned that any reaction where electrons move around from atom to atom is a redox reaction, that oxidation is the loss of electrons, and that reduction is the gain of electrons, and that oxidation numbers are assigned to atoms to take part in reactions in order to keep track of what their electrons are up to. You also learned a few simple tricks to help figure out what an atom's oxidation state is, and you got a little practice figuring out how to assign oxidation states and balance oxidation reactions with 2 examples, one pretty simple and another a little less so. This episode of Crash Course Chemistry was written by Kim Krieger.
Alrighty. So that probably went a little bit more in depth than I think you guys are probably going to go to in the NLN, but just in case, I figured to give you a whole video, you should understand what oxidation states are now, and all of that. Okay, and those rules talked about in the beginning, those rules for assigning the oxidation states, you probably need to know. Those are actually on the list of 7 rules, or 8 rules, I'm not too sure. But it's on your packet, under the oxidation reduction section. So whenever you're going through your problems with that, just go along with those rules. Literally just read each rule individually and just go from there. It should be fine. It's not too bad. All right, so phases of matter is something that's probably a little bit more familiar to people. So you have solids, liquids, and gases. And solids are crystalline. They're fixed. They don't move. And the particles are very tightly close together. Liquid, the particles have a little more of like a free room. They can kind of range around a little bit. They don't have a definite shape. And they're more phase between molecules. And with gases kind of go all over the place. There's no definite shape. They don't have a particular volume either. And there's lots of space between the particles for them to go ahead and collide and give reactions for. So a phase change diagram, these are really important to know. They show you how a compound is going to go from a solid to a liquid to a gas, and at what temperatures it's going to take for your compound to go do that. So in order to read this, what you would look at, and they're different for each compound. So let's take water, for example, because everybody knows water, right? So here, it's a solid. You're going to keep adding heat to it to keep increasing the temperature. You're going to finally get to the melting point of water. So as it melts, like if you have a glass of ice water, fun fact, that ice water is always going to be at the same temperature until all the ice melts. Then it's going to be going and gaining temperature while it's a completely liquid until it gets to like a boiling point, which would be this point over here. So that pot of boiling water is always going to be at 100 degrees, or the boiling point, until it's all gone. All right? And that's all that this says. It just says at what temperature you reach that boiling point, and you remain the same temperature throughout the entire time. Same thing for the melting point. So if they give you this diagram and they ask you to determine that from the graph, given a different compound, then you can go ahead and pick the boiling point and melting point according to the temperature over here and the heat required to get it up to that next phase change. So the other example I have over here is the example of why it takes longer to cook things at a higher altitude. So your boiling point decreases as your pressure decreases. So they give you the other example of water, of course. So if you're over here at sea level, I think this would be sea level, I think, you're boiling at 100 degrees. If you're going up into the mountains, you're then going to be boiling point at this line, at this point of your X of 92, and then your Y point is going to be 760 or so, and then that's going to be the boiling point of 92. So therefore, your boiling point at different elevations, different pressures. All right? So solutions. So for your solutions, you have a solute, which would be like your sugar, putting into your solvent, which would be the water, in order to make this solution. So solvent is going to be stuff you're putting the solute into. U comes before V in the alphabet, so there's that. A tincture is a special type of solution in which a solvent is alcohol. That's one of the terms that you guys need to know for your NLN. It's not definition. Homogeneous versus a heterogeneous mixture. So homogeneous mixture means something you can like pick apart or pull apart. So there it goes. They're separated by filtration due to differing sizes and chemical composition from the materials present. They're not chemically combined, in other words. So the heterogeneous mixture would have separated by chromatography or distillation. And they have the same properties throughout the entire solution. So solubility is the ability of a solute to dissolve in a particular solvent. Emulsion is one of the terms they ask you to know too for the NLN. So emulsion is when a liquid is dispersed in another liquid which it's not soluble. The example they give you here is water and oil. They are not going to be mixed. However, if you add in an emulsifier, which mustard would be the emulsifier, it's going to allow the two to go ahead and mix properly. A chemical change. A chemical change is whenever compounds are going to combine to create a new compound. So the oxidation of a Statue of Liberty is an example. Color changing of leaves, and anything that burns are all examples of chemical changes. So it says here the Statue of Liberty was copper, and the oxidation of it makes a copper oxide, which gives the Statue of Liberty its green color. A physical change is going to be anything that can be reversed, essentially. So the product is not a chemical composition from substance. So the water over here, for example, you can take this water from this little cup and you pour it back into an ice cube tray, and you can make it back into an ice cube. That pencil, you can put the little pieces of the pencil back together, and etc. There's common tests to test for certain chemicals, and if you have a chemistry lab, general chemistry lab, you should go through all of these. And they're all going to be up here on the PowerPoint. You have Felling's test, which is a test for aldehydes and monosaccharides. A monosaccharide is biochemistry term. We're going to learn about later. The reaction is going to be deep blue. It's going to turn red when the aldehyde or monosaccharide is present. Here's the example of that right here. Litmus paper is going to be a test for acids and bases. So red litmus paper turns blue when the base is present, and then blue paper is going to turn red when the acid is present. Here's a picture of what it looks like over here. According to hydrochloric acid, that's an acid that's being put on there. Brownfield blue is going to test for CO2 and acids, and it's going to change colors from blue to green to yellow in the presence of CO2. Here's it with 1 drop of the indicator, and then here's it with 2 drops of the indicator to give it a little more of a pigment. The other one is going to be called the Lugol solution in iodine. It's going to test for starches, and it's going to turn from rust color to blue or black in the presence of a starch. Benedict solution is another example over here. It's going to be testing for simple sugars, and it's going to turn red when heated with a simple sugar. Oops. And the philanthropin test over here tests for acids. That's actually a really fun one to do whenever you're doing your chemistry lab. It's called the titration lab. And you're going to be, what you do is you drop acid into a base, and whenever this indicator turns up, it means that there's excess in the solution to turn it pink. And it's going to test for excess acid. Now, electron configuration. There's a couple of ways to do this. I like doing this regular basic way over here. I'm just going to be with the s, p, d, and f orbitals. If you're asked to do this on a test, which you probably will be, there's a shortcut way, which I have a video of to show you the shortcut, and this is the long way. So what you guys are going to do is you're going to All right, you're going to list out your numbers 1 through 6. This actually goes to 7, right? Oh, this one goes up to 8. Okay. Then you're going to do 2, 3, 4, 5, 6, 7. Then you're going to come over here to the 3 column. 3, 4, 5, 6. Can you guys see that? A little better? All right. And then we just write 4 and 5, which you shouldn't get into these high numbers over here as the pyramid kind of goes on. See, it makes a nice little pyramid there? All right, so your first row is going to be S's. We can fill in S's down this whole column. Your P's are going to be next. Your D's are going to come after that. And then we get into the F's. And how this works is it's going to increase by 4 each time. So, as you guys can see from the PowerPoint, over here on this chart, S subshells over here can all hold 2. P subshells are going to increase by 4 to give you a maximum of 6 electrons. D subshells are going to be 10, and then F's are going to be 14. Now, if you're given an element without a charge, the number of protons should equal the number of electrons if it's just a neutral, no charge element. We'll take, for example, let me go ahead and find one. Go ahead and take oxygen, for example. Oxygen's number 8. So if oxygen is uncharged, that means it has 8 protons, therefore it should have 8 electrons, right? And you're going to fill this in as the picture there shows, all through it like this. All right, they're going to kind of go in a diagonal. And what this does is, long story short, it goes through the lowest energy. Everything wants to be at its lowest energy. Nothing ever wants to get all hyper and crazy. So if it's at its lowest energy, this is the flow of what it goes to. So I'm going to go ahead and count along until I get to 8. So my first stop over here is 1s. 1s has 2. That's 1, 2 electrons. Next stop is going to be the 2s spot. That's going to hold 2. Now we're at 4 electrons. All right. Next up over here is going to be P. They can hold a maximum of 6, but I only need 4. So I'm going to do 1, 2, 3, 4. I'm going to stop. Now I have 8 electrons on my paper. And I'm just leaving me with 2p4. All right. And that's how that whole thing is going to go. So there's, as you're going to see in the video, the shortcut way to do all of this stuff is going to be going from the blocks of the periodic table. Another good reason why you guys should all know how to use your periodic table and know all the information provided for it. So you're going to have the S block, the D block, F block, and P block. Once again, S's can hold a maximum of 2, P's can hold a maximum of 6, D's can hold a maximum of 10, and F's can hold a maximum of 14 before you jump to the next orbital. And remember, they're all filling in this configuration, which I said, long story short, is just the lowest energy configuration. Trust me.
Hello, and welcome to another edition of Mr. Chappell's Chemistry Screencasts. Today we're going to learn about electronic configurations. What you'll learn in this screencast is how to label a periodic table for electronic configurations. You'll also learn how to find the electronic configuration for any element. Now, there are a couple of things you're going to need. You're going to need a periodic table, and you're going to need some coloring pens or pencils. Let's go ahead and get started. Well, here we have our periodic table, and the first thing we want to do is we want to label down the 4 blocks of the periodic table. That's the S block, the P block, the D block, and the F block. So let's start with the S block. And the S block includes families 1 and 2, and you have to remember to include helium with that. It's actually part of the S block. The next block we're going to label is the P block. And that includes everything from family number 13 all the way to family number 18. And in the middle, we're going to have the D block. And that includes all the transitional elements. And for our last block, no prizes for guessing, this is going to be the F block. Now the next thing we need to do is we need to label down some numbers next to each of the blocks. Let's start with the S block. We want to put the number 1 next to hydrogen, number 2 next to lithium, and stop me if you see a pattern here. We go all the way to number 7, francium. Now for the P block, we're going to start with number 2, and that's going to be next to boron. And it's probably a good idea to put the 2, or put all these numbers, that is, right on the line. Next to aluminum of 3, next to gallium of 4, 5, 6, and then lastly a 7. For the D block, we want to put a number just to the left of scandium, number 3, number 4, number 5, and number 6. And lastly, for the F block, we want to put a number 4 next to cerium and a number 5 next to thorium. Now let's go through with a couple of examples. Here we are, and the first electronic configuration that we're going to write out is for the element oxygen. That's number 8. And what we need to do is start immediately to the left of hydrogen and go forward by atomic number until we land on oxygen. So we're going to go hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. So the first number we run into is a 1. We're at the S block, so we write 1s. We're going to cross 2 elements, hydrogen and helium, before we run into our next number. So we write 1s2. The number we run into is a 2. We're at the S block, so we write 2s, and we cross 2 elements until we run into our next number. So we write 2s2. The number we ran into is a 2. We're at the P block, and we just have to count over to oxygen. 1, 2, 3, 4. So we write 2p4. It's important to include the element that you're shooting for in that count. Now the next example we're going to do is for silicon. Silicon is number 14, and that's going to be a lot of terms, but we don't need to write them all down. We're really just interested in the valence shell. So what you do is you find silicon, and you count backward by atomic number until you run into your first inert gas, which is going to be neon. And you write brackets neon. That represents 10 core electrons. They aren't going to do very much, so we're just going to abbreviate them. And then you start the process from there. The first number we run into is a 3. We're at the P block, so we write 3p2 because we've crossed 2 elements. And the next term we run into is a 3. We're at the P block, so we write 3p1, and then finally 2 with silicon. Now for zirconium, number 40, we're also going to back up until we run into our first inert gas. And the first inert gas we run into is going to be krypton. So we write brackets krypton. Then we start from krypton, we go to 5s2, and then finally 4d2, ending with zirconium. Now for xenon, number 54, you might think that's pretty easy. It is an inert gas, so we just need to write down bracket xenon. But unfortunately, the rule is you have to spell out the valence shell, even if it's not going to be doing very much. So we need to start at xenon and back up until we run into our first inert gas. And that first inert gas is going to be krypton. So we write down brackets krypton, and then we write 5s2, 4d10, and then finally 5p6 with xenon. Now for our last example, I picked the hardest one, or one of the hardest one. This is Mr. Mercury, number 80. And once again, we back up until we run into our first inert gas, and that's going to be xenon. We write brackets xenon, 6s2, 5d10. Now you might think that we're done, but you'll notice right here there's a gap in the atomic number between 57 and 72. So we need to tack on one last term. We need to go find 58 and write down 4f. And we're going to cross all the f's, and there's a total of 14 of them, before we go back to number 72. So our last term is 4f14, and then you're done, and that concludes our lesson. But wait, there's still more. By popular demand, I'm now adding a joke to the end of each screencast. Here's today's joke. What do electrons and hamburger have in common? Well, they're both in the ground state. Get it? They're both in the ground state.
Cute. Very cute. All right, and one last thing I want to touch on before we jump ahead to organic chemistry. We're in the last stretch. We're going to do a little bit of organic, and then we should be good. I wanted to go ahead and show you guys how does electrons fill. So we had the example what I did with oxygen, and it filled up to give us a electron configuration of 1s2, 2s2, 2p4, right? Saw that same thing in the video earlier. So we said that the S block is able to hold 2 electrons. Each of these lines can hold a pair of electrons. Same thing with a bond. S is going to have 1 line. P, they said they can have 6, right? 6 max. So I can do 1, 2, 3. Give me room for 3 pairs, aka 6 electrons. Now, electrons want to fill in their lowest energy state. Think about seats on a bus. If you're going onto a bus, you're not going to go sit next to a perfectly stranger if there's a bunch of seats open, right? So they're going to fill in an order. These are already full because they can only hold 2. They have upward and downward spins because of like quantum theory. We're not going to get into. But so it's upward and downward spins. These are its orbitals. So if this 2p has 4, what we're going to start doing is we're going to start filling them one by one. As in 1, 2, 3. Spots are all full now, coming back around to this 4. Leaving us with 2 of these open. So this is wrong. Lowest energy form. No seats open. Okay? That's going to be on the back of your worksheet. Alrighty. So we're going to go into organic chemistry. And organic chemistry is basically anything that contains carbon. All right? And I always chuckle and everything's like, oh, it's organic. I'm like, well, of course it is. It's made of carbon. Like, it's lettuce, you know? So, examples of organic compounds would be hydrocarbons, alcohols, aldehydes, ketones, ethers, and esters. When you actually take an organic chemistry course, this is going to be your meat and potatoes. What this is your different organic chemicals and their reactive groups. So these R's, like you saw from earlier, they just mean like a giant carbon compound that's unreactive. The only reactive part is whatever is in this little structural formula. All right? So you say RCOH, therefore the reactive part is this carboxyl. Right here, for example. So in your packet, whenever asked about an aldehyde, therefore you know the structure of that, or an ester or an ether, you know what the structures are going to look like with their reactive groups. And here's a couple of examples of their structural formula. Like ethanol, for example, this C's and H's, this is your R. So your alcohol, the only reactive part of that is the OH. where it says ROH. Going back down, this is your R, that C compound, and this is your OH. This is a general hydrocarbon over here. An aldehyde would have your HCH double bond to O. Going back up over here is your R double bond to OH. All right? Different stuff about that. So biochemistry is the chemistry of living things. There's three main groups. There's carbohydrates, lipids, and proteins. So carbohydrates are monosaccharides. They're going to be things like simple sugars, like glucose, for example. Disaccharides are what it means two. Even two monosaccharides. Their example is going to be sucrose. And there's polysaccharides, poly meaning many, which have many sugars, like complex sugars like starch. Lipids are fats and steroids. We have 3 fatty acids and 1 glycerol, which makes a lipid. And a protein is made up of a string of amino acids. There's 20 different types of amino acids. And these sequences are going to determine the properties of proteins. When you take a biochemistry course, this is going to be meat and potatoes, which are the 20 common amino acids, the things that make up proteins. If you ever take one of these, you're going to have to memorize this chart inside and out. So if you see anything on your nursing exam about the leucine or valine, arginine, whatever the case is, I'm sure you can refer back to this table. I'm not sure if I might make you memorize it for this test. I didn't see anything in the sample questions that was that complicated. But this is what's going to make up DNA, for example, different kinds of proteins, structures, peptide acids, and stuff like that. Organic chemistry reaction types. There's a dehydration type, which is taking out of water or dehydrating the reaction. And hydrolysis then is the opposite of that, which is adding in a water to give you the reverse reaction. So one is taking out of water, one's adding in a water to break up the compound. All right, a couple sample questions. Which of these groups of chemicals is not normally found in most living things? Carbohydrates, proteins, so, see? Okay, good. Number 2, which of these formulas represents an alcohol? Did I hear a D anywhere? Because the answer is D. I heard a couple of C's. C's come from the COOH, the carboxylic, going back to the chart over here, whereas it's a carboxyl, which is your RCOOH, that's a carboxyl. So it could be a little bit tricky. All right, and if you have the following unbalanced equation, what is the coefficient of the ammonia in the balanced equation that has the smallest whole number coefficient? Two. What is the coefficient of ammonia in the balanced equation that has the smallest whole number coefficient? Okay, so what it means by the smallest number coefficient is that it is the simplest. Because if you have 2 nitrogens over here, take inventory. You have 2 nitrogens over here, 2 hydrogens over here. You're then going to have 1 nitrogen over here and 3 hydrogens over here. If you wanted to go ahead and balance this, I would start with the nitrogens first. So you'd have 2 over here. I can put a 2 as its coefficient to multiply this thing through to give you then 2 nitrogens, and then 2 times 3 would be 6 hydrogens. And then you'd put a 3 over here in front of this H2, because 3 times 2 would be 6. So therefore, that would make that a balanced equation. And like I said, there's a whole bunch of examples in that packet. Sample question 4. Which of these represents a non-polar covalent bond? Now we said covalent bonds are 2 nonmetals, first of all. So we can cross out your sodium because that's a metal. Also, they have to be pretty even with the hogging of electrons. So it would be A, correct, because bromine's kind of hogging all these electrons from that hydrogen over there. All right, last one is question number 5. Hydrogen can be prepared in the laboratory by combining zinc and HCl. And the resulting reaction, the metallic zinc, is either charged to another element or changed to another element, reacts with water in the acid. replaces the combined hydrogen in the acid, or serves as a catalyst? C, correct. This is what was going to be the single replacement reaction, where you're going to have zinc plus HCl, and they're going to be swapping partners, like how you saw with the Flintstones. So then you're going to get zinc chloride and then some kind of hydrogen. All right. Lots of practice, though, so just go ahead and go through your book. It has a lot of sample questions. They gave you some sample questions out here from the ASC. If you guys have any further questions, myself or anybody else from the chemistry department over at the ASC can help you. We're always willing. We're located on the 3rd floor of the library. All right, please fill out the forms, the evaluation forms. I'd love to hear all your comments. Leave them in the back. And thank you guys for coming so much. Hope you guys learned some stuff about chemistry. It's pretty cool. Right? Yeah, it's good stuff.